So it's my pleasure to introduce Kyoung Seog Lee from the Institute of the Mathematical Sciences of the Americas, which is at the University of Miami. He is speaking today on derived categories and motifs of moduli spaces of vector bundles on curves.
Okay, thank you very much. Thank you very much for the introduction and the invitation. It's my great pleasure to give this talk. So today I'm going to talk about derived categories and motifs of moduli spaces of vector bundles on curve. And this is based on joint works with several joint works with Indrani Biswas, Thomas Gomez, and Han-Bon Moon and MS Narasimhan. Okay, let me start. So let me first begin from basic things. So let C be a smooth projective curve of genus G, and I will walk over C today. So yeah, we want to classify vector bundles on C, and when there is a continuous family, we want to understand this parameter space. So when genus is 0, so when C is P1, then Grothendieck classify vector bundles on P1 by showing that every vector bundle is a direct sum of line bundles on P1. So on genus 0, the vector bundles are completely classified. And when genus 1, Atiyah proved that for the set of indecomposable vector bundles on C is of a given length and degree is isomorphic to C. So in this sense, he also classified indecomposable vector bundles on C. So today I will concentrate smooth projective curve of genus greater than or equal to 2. And then Mumford proved that the set of isomorphism classes of stable vector bundles of length R and given degree D on C form a smooth quasi-projective variety of dimension R squared times G minus 1 plus 1. So he proved that, this set of isomorphism class form this nice variety. And this, moduli space of stable vector bundle on curve has a natural compactification. And this is a cosmoduli. When I compactify this space, I need to introduce this notion of S-equivalent classes and the semi-stable vector bundles. Anyway, it has a natural compactification, and Sheshadri proved that this compactification is a normal projective variety. And then Narasimhan and Ramanan proved that this variety is not smooth in general. So this is just normal projective variety. This moduli space of length R and degree D, semi-stable vector bundles on C is just a normal projective variety. And Narasimhan and Ramanan proved that the smooth locus is exactly the locus of a stable vector bundle, except this R equals G equal 2 case, and D is even number. So, except this case, this moduli space is, the smooth locus is exactly the stable vector bundle. So when R and D are co-prime, then this semi-stability is equal to stability. So this moduli space is a smooth projective variety. And we have a natural map from this moduli space to Jacobian, which sends a vector bundle to its determinant. So this is very natural map. And so I fix a line bundle L here and consider its fiber. So this becomes the moduli space of vector bundles, stable vector bundles of length R, and this determinant is isomorphic to L. So this is our main object today, indeed. So I will consider this moduli space of length R, stable vector bundle of length R and determinant L. And the Ramanan proved that when R and D are co-prime, then this variety is indeed a smooth projective Fano variety of index 2. Okay, so is there any question so far? No. Okay, let me keep going on. So let me start from, as I told you, this is our main object today. So let me consider first to start from how we study the derived category of this smooth projective Fano variety. So yeah, let me record the setting. So let R be an integer greater than or equal to 2, and D another integer, which are co-prime to each other. So then this becomes a smooth projective Fano variety of index 2. And yeah, this C is just a smooth projective curve of genus greater than or equal to 2. And then this moduli space is nothing but rank R stable vector bundles whose determinant are isomorphic to L. And then in this case, it is well known that there is a Poincare bundle on C times M. So then, I mean, I have this natural vector bundle on this space. And then using this Poincare bundle, I can define so-called free M-Chi transform. So I have a shift here, and then I pull back this shift to this C times M. And then I push for, I pull back an object here and to here, and then tensor with this Poincare bundle and push it to this M. So there's so-called free M-Chi transform, which is a functor from derived category, bounded derived category of C to the bounded derived category of M. And then natural question is whether this is a fully faithful or not, or in other words, whether this is an embedding or not. So this is quite a natural question. And for length is equal to 2 and degree is equal to 1, and Narashima and Kuznetsov independently prove that the derived category of this curve can be embedded into derived category of this moduli space via this free M-Chi transform. So this in other words, this free M-Chi transform is fully faithful. And I mean, von Alpha and Kuznetsov proved this for hyperelliptic curve case and using deformation argument to prove it for general curve case. And in the Narashima proved all the cases using this Hecke modification. So anyway, for genus, for rank equal 2 case, and this we have anyway this embedding for any curve. Okay, then why this embedding is important? Let me explain why this embedding is important. So there's no so-called there's a notion so-called semiorthogonal decomposition. So let me record the notion. So let T be a triangulated category. Then a semi-orthogonal decomposition of this triangulated category T is a sequence of 4 triangulated subcategory A1 to AN satisfying the following property. So first property is saying that there's no home from back to forth. So I mean, if I have an element small ai in this curly ai and the small aj in curly aj, and then when suppose that I is greater than j. So I mean, yeah, AI is here and AJ is here. And then, I mean, the first condition says that there's no home from this large A to small, this AI to AJ when I is greater than J. So I mean, when I write this category in this order, then it means that there's no home from back to forth. And the second condition is saying that these subcategories generate the whole category. If these two conditions satisfy, then I will say this triangulated category admits a semi-orthogonal decomposition. And I will write in this way to say that so T admits the semi-orthogonal decomposition whose component is this AI. Okay, so there are many examples indeed, but the most relevant example today is that maybe this one. So Bondara and Orlov prove that when C is a curve with genus 2, then this moduli space of this length 2 and degree 1. So I always assume that this rank and degrees are co-prime. So in this length is 2, then I can assume that degree is 1. Okay, so anyway, when length is 2 and degrees is this line bundle of degree 1, then this proved by many people. For example, Newstead and Narashima Ramanan and Mukai prove that this moduli space is nothing but intersection of two 4-dimensional quadric. So this is intersection of two 4-dimensional quadric. And so this is a 3-dimensional Fano variety with index 2. And Bondara and Orlov prove that so this intersection of quadri, derived category of this intersection of two quadri has the following semi-orthogonal decomposition. So it has two copy of derived category of point and one copy of derived category of curve. So they prove that there is such a semi-orthogonal decomposition. Okay, is there any question so far? No. Okay, so, and then, so this embedding, the derived category of curve is embedded into this derived category moduli. So, this implies that this derived category has a semi-orthogonal decomposition whose component is derived category of curve, right? This case. So, this embedding, indeed, this curve is embedded into Fourier transform again. And so this theorem says that the derived category of moduli space admits a semi-orthogonal decomposition, and one component is equivalent to derived category of curve. That's this. That's one implication of this theorem. So then, it is a natural question, an important task to understand the full semi-orthogonal decomposition. So this SOD means semi-orthogonal decomposition from now on. So it's an important task to understand this full semi-orthogonal decomposition. I know that already one copy of curve is embedded into moduli space. And because moduli space is Banach variety of index 2, I already know that two copy of points are there. So these two copy of points and one copy of curve is there. But the natural question is what are the other component? Obviously, these two copy of points and one copy of curve cannot generate the whole category. So the natural question is what will be the remaining semi-orthogonal components. Okay, then there's question, conjecture by Narashman, and independently Bellman, Galkin, Mukopadia. They conjecture that the derived category of moduli space, when length is equal to 2, will have the following semi-orthogonal decomposition. So they conjecture that the derived category of M will have the following semi-orthogonal decomposition, which says that which consists of two copy of points, two copy of curve, two copy of second symmetric product, and keep going on, and the two copy of G-2 symmetric product of curve, and one copy of G-1 symmetric product of curve. So this is they conjecture. So let me show kind of proof why this is reasonable conjecture. But anyway, they made this conjecture. And you see that this conjecture is true when genus is equal to 2, because there are two copy of point and one copy of curve. Okay, so as I told you, I will show some kind of evidence. And recently there has been lots of progress in this direction, but let me explain that part later. But in any case, before that, Professor Narashman asked us that, when he made his conjecture, he asked, can he further decompose this above conjectural decomposition? So we suppose that we have this decomposition. Then he asked whether we can further decompose this decomposition, this component. So Biswas, Gomez, and I were motivated by his question and studied that. We conjecture that when K is from 1 to G-1, then derived category of K symmetric product, this is K symmetric product of curve, will not admit the non-trivial semi-orthogonal decomposition. So in other words, we conjecture that this semi-orthogonal decomposition cannot be further decomposed. So it's kind of a irreducible one in a sense. Okay, so we conjecture that, this K-symmetric product will not admit the semi-orthogonal decomposition. And then how we can prove this is the case. So in order to prove that, the best tool was a theorem of Kawatani and Okawa. So let me explain what is their theorem. So let X be a smooth projective curve such that the base locus of a canonical divisor is a finite set. Then they prove that the derived category of X cannot have a non-trivial semi-orthogonal decomposition. And they also prove that when S is a minimal smooth projective surface of general type with many global section and satisfying the base locus, one-dimensional components of base locus has negative definite self-intersection and negative definite intersection matrix, then they conjecture that, they prove that the derived category of surface does not admit the semi-orthogonal decomposition. So anyway, the key point is that in order to prove that a derived category of coherent shapes on a variety does not admit a semi-orthogonal decomposition, we need to study the base locus of canonical divisor. So it is quite natural to study the base locus of canonical divisor of K-symmetric product of curve. So Biswas, Gomez, and myself proved that when K is from 1 to G minus 1, then the base locus of this canonical divisor of K-symmetric product is the set of a point in this symmetric product such that the global section is, the dimension of global section is greater than 1. In other words, the base locus is the set of points in symmetric product where this Arban map to Jacobian is not injective. So, I mean, we have this complete description of this base locus of canonical divisor for symmetric product of curves. And using this description, we can prove the following result. So first, Oka himself, and it also follows from his theorem with Kawatani, that so Oka proved that the derived category curve does not admit a non-trivial semi-orthogonal decomposition. And using our description of this base locus, Biswas, Gomez, and myself proved that the second symmetric product, derived category of second symmetric product does not admit a non-trivial semi-orthogonal decomposition. And moreover, we also proved that when K is from 1 to gonality, then the K-symmetric product does not admit a non-trivial semi-orthogonal decomposition. So in this range, we proved that this derived category of K-symmetric product does not admit a non-trivial semi-orthogonal decomposition. And later, Bastianelli and Bellman and Okawa and Ricolfi proved that they use kind of deformation argument to prove that the third symmetric product does not admit a semi-orthogonal decomposition when genus is 4. And they also proved that in this range, the derived category of K-symmetric product does not admit a non-trivial semi-orthogonal decomposition. So please note that this gonality of a curve, gonality is the lowest degree of all maps from, I consider all maps from C to P1, and this is lowest degree among all this non-constant morphism. And for generic curve, this gonality is this number. So anyway, we proved that almost the half of this K-symmetric product from 1 to K minus 1 does not admit a non-trivial semi-orthogonal decomposition. And then recently Lin proved that, Lin studied this. So, in order to, so far, the theorem of Kawatani-Oka proved that this base locus of canonical divisor. So this is, this is studying, linear system of canonical divisor. But he changed the viewpoint and he considered this intersection of base locus of line bundles that are isomorphic to canonical bundle in a Néron-Severi group. So he studied numerical equivalence class instead of, linear equivalence. And then he can strengthen the result. So he proved that. So when genus is greater than or equal to 2, and when K is from this range, then the derived category of K-symmetric product does not admit a non-trivial semi-orthogonal decomposition. And he also proved that the product of this case, these symmetric products and abelian variety also does not admit a semi-orthogonal decomposition. So anyway, what I want to say is that, so when we have this semi-orthogonal decomposition, then this cannot be further decomposed. So this is kind of a kind of analogy of expressing one representation by direct sum of irreducible representation. So it's very rough analogy, but anyway, So anyway, so now we know that the derived category of this component, this semi-orthogonal component, cannot be further decomposed. Okay, so is there any question? Okay, let me go further. Okay, so then let me give a kind of evidence why this conjecture is a reasonable conjecture in a sense. So in order to do that, let me recall the notion of motif. So Grothendieck, I mean, after establishing several Bayes cohomology theory, Grothendieck wanted to understand why these Bayes cohomology theory behave in a similar way. So he conjectured that there will be a category of motif M and a functor from the category of smooth projective variety to this motif, such that this every Bayes cohomology theory H should factor through this small h. So I mean, he wants to explain why all these Bayes cohomology, which are defined in a completely different way, behave the same way, and he expects that there must be some category or motif such that this every Bayes cohomology functor should factor through this category motif. So for example, if I want to prove Q-ness formula for this Bayes cohomology of a smooth projective variety, then he proved that this Q-ness formula holds in the category of motif. So this implies that every Bayes cohomology should satisfy Q-ness formula, something like that. So he explained the behavior of this common behavior of Bayes cohomology in this way. And so indeed, there are several versions of motif these days. So indeed, Grothendieck himself developed the theory of Chow motif, and it was later, I mean, further developed by Manin. And Berlinson and Dallin proposed there must be kind of mixed motif. So this is a kind of, so Chow motif works for smooth projective variety, but in order to generalize this notion of motif to, quasi-projective variety, which can be singular, then we need the notion of mixed motif. So Berlinson and Dallin proposed there must be such category. And then later it was established by Hanamura and Levin and Voevodsky independently. And but what they constructed is the so-called triangulated category of mixed motif. And I mean, still there are many people working on to construct this mixed motif. Okay, so anyway, I will explain several brief construction for this category. And the baby version of motif is so-called Grothendieck ring of varieties. So let variety be the category of varieties of C. And then the Grothendieck ring of variety is nothing but the free abelian group generated by X. X is a class of algebraic variety, modular some relation. So this relation is nothing but this variety is equivalent to X minus G plus G, and G is a closed subset of X. So if I consider this pre-abelian group generated by this isomorphism class of variety and model out this group by relation, then I obtain the Grothendieck ring of variety. And recently there has been lots of works studying this mysterious group, and there's a natural product structure given by Cartesian product. So this become a ring. So anyway, this is baby version of motif. And
can I ask one quick question?
Yeah.
So when you say varieties there, they don't need to be projective, they don't need to be quasi-projective. Yes.
Variety, yeah. So I mean, for this definition, yeah.
Abstract variety, yeah.
Yeah, this is just the abstract variety. Yeah. Okay. But there is some presentation, another presentation. So one can, I mean, consider only smooth projective variety, and the relation comes from blow-up relation. So there are another, I mean, I can, how can I say, consider the generator by only smooth projective variety. Anyway, for this definition, I don't need X to be quasi-projective. So this is just a variety. Okay. Is there any question? Okay, let me keep going further. So yeah, this is kind of baby motif. And then Grothendieck himself developed the notion of Chow motif. So, I mean, he considered this category of correspondence varieties. So this object is smooth projective varieties of C. And the morphism from X to Y is nothing but this Chow group. I consider element in Chow group in X times Y. And then, I mean, this is category of this correspondence. And then the category of effective Chow motif is nothing but pseudo-abelian closure of this correspondence and the category of correspondence. And the category of Chow motif is nothing but obtain this, I mean, by inverting Lefsetz motif in this effective Chow motif, I obtain this category of Chow motifs. So, I mean, the definition itself is quite easy. And again, yeah, so as I told you, so then one can consider this notion of mixed motif. So Berlinson and Lean conjecture that there must be some abelian tensor category of mixed motif satisfying some property. So I mean, so it should reflect some theory of mixed dot structure, and this should be deal with smooth and singular quasi-projective varieties. So as I told you, there are several constructions, and but still this construction of abelian category is mysterious as far as I know. So anyway, so they conjecture that there must be some abelian category satisfying certain property, and there are lots of works. But the key point is that Berlin suggests that so constructing this mixed Arch structure, abelian category mixed Arch structure is difficult, but he suggests to construct the derived category of this mixed Arch structure. So then Hanamura and Levin and Boyedowski suggest this construction of triangulated category of motif independently. So, I mean, so yeah, the construction itself is also quite easy, but of course dealing with it is quite difficult. But anyway, I mean, this there's quite similar construction. So this smooth correspondence means that the object is category of smooth scheme over field, and the morphism is algebraic cycle over this product, where this component, each component of G is finite over this X. And then one can prove that this is an additive category, and addition and tensor product is defined in a natural way. And then I want to impose that this homology theory do not change on the product of A1. And I also want this Meyer-Beatrice type property. So I consider the homotopy category of this additive category of smooth correspondence, which is defined here. And then I consider this homotopy category, and then I model out this by these two relations. Then I obtain the triangulate category of motif. Of course, I need some categorical procedure, but anyway, one can define the triangulated category of geometric motif in this way. Okay, and then as I told you, this category of motif can deal with singular varieties, and also it has a benefit because it can also deal with algebraic stack. So I mean, I can define the motif of a stack, which will be very useful later. And this triangulate category of this geometric motif has several nice properties like finesse formula and homotopy invariance. Homotopy invariance comes from this relation, and the Meyer-Beatrice also comes from this relation. Because I model out by this relation, this category naturally has this property. And Boyedowski also proved that this theory of Chow motif is related to the theory of triangulated category of geometric motif. And Bondarko proved that the Grothendieck ring level, it is isomorphic. So yeah, anyway, I told you there are three versions of motif: the Grothendieck ring of variety and effective Chow motif, and this triangulated category of geometric motif. And yeah, so I mean, and later I will deal with the motif of stack. So I need some kind of completion. So I mean, let me skip this part. But when you know this motivic integral theory of motivic integration, I need to deal with a certain completion. So this is I mean, it's the same analogy of this completion in theory of motivic integration. So anyway, I can do this dimensional completion, and then I can deal with this Grothendieck ring of variety. I mean, completion of Grothendieck ring of variety to deal with this motif of stack. Okay, so let me skip this part, but I mean also we can do the same things for this Grothendieck ring of, I mean this Voevodsky's motif and Chow motif in a similar way. Okay, is there any question so far? So anyway, what I told you is I have 3 versions of motif and I have a completion. That's all I want to say. Okay, then let me go to the point. So why I'm saying all these things? The Orloff conjectured that the derived category of coherent shapes and motif of algebraic variety will be closely related. So to be more precise, he conjectured that let X and Y be 2 smooth projective variety having equivalent derived category. Then he conjectured that motif of X and motif of Y should be the same. So this isomorphism is indeed the isomorphism in Chow motif with Q coefficient. But anyway, let me skip that part. But anyway, the slogan is variety having same derived category will have the same motif. And he also conjectured that when X and Y are 2 smooth projective varieties such that derived category of X is embedded into derived category Y. So then he conjectured that the motif of X is embedded into motif of Y. So the slogan is equivalence of derived category implies the isomorphism of motif, and embedding of derived category will imply some embedding in the level of motif. That's what he expected. And recently, Kuznetsov and Shindo also proposed a conjecture in the same spirit. So when X and Y be 2 smooth projective variety, simply connected smooth projective variety, having same derived category, then they conjecture that the difference between X and Y in Grothendieck ring should be a 0 divisor in the ring of Grothendieck variety. Grothendieck ring of variety, and the difference should become 0 when I multiply certain power of this affine line. So, and all the known example of Grothendieck 0 divisor in the Grothendieck ring of variety, which is become 0 when I multiply this affine line of variety. As far as I know, all example comes from this case. So these 2 have same derived category. So in other words, so there are several evidence showing that the derived category and motifs should be closely related. So that's one key idea for my talk. So, and okay, let me record that Narashman and Bellman-Galkin-Mukhopadhyay conjectured that the derived category of moduli space will have semi-orthogonal decomposition, which consists of 2 copy of points, 2 copy of curve, 2 copy of second symmetric product, up to 2 copy of G-2 symmetric product, and 1 copy of G-1 symmetric product. And what I proved that is that for any semi-simple category of motifs, there's following decomposition. So this motif of this rank 2 vector bundles on this curve has this, k is from J0 to G-2, and because I have 2 left such motif, this means that 2 copy of this curve. So in other words, this motif of this moduli space has 2 copy of point, 2 copy of curve, up to 2 copy of G-2 symmetric product, and only 1 copy of G-1 symmetric product. So I proved that for any semi-simple category motif, there's compatible motivic decomposition of this moduli space of vector bundles and curves, where length is equal to 2. Sorry, I just see.
Yeah, there's a question by Angel on the chat on whether the opposite direction, I think, of the conjecture holds.
I see. I think it's not known. I think I think the question is whether the difference of 2 variety, difference of classes of 2 variety in the Grothendieck ring of 0 divisor of this affine line, then I think it's not known. Yeah. So yeah, I don't know. Yeah. Thank you. Thank you very much for the question. Yeah, is there any further question? So yeah, if there's no further question, let me keep going on. So I mean, so this anyway gives the first evidence of this conjecture. So this derived category has this semi-orthogonal decomposition. And I use Banner's works. So indeed, Banner already studied the motif of this moduli space. And what I prove is that his description implies the following decomposition. So I basically use Banner's decomposition, Banner's works. But later, Gomez and myself give completely different proof of this result. And so indeed, Banner's work study using this tedious flip to obtain this motivic description. But I mean, we use the motif of stack to prove this and some Hado-Narasimhan filtration to obtain this motivic decomposition. And so we found a much more conceptual way why this motivic decomposition should exist. And independently, Bellman and Galkin and Mukhopadhyay obtained similar decomposition in the Grothendieck ring of variety. So anyway, there are lots of evidence that there should be such decomposition. Okay. So anyway, so motivic decomposition, I mean, indeed, the motif of this moduli space has been studied for many years. So, but derived category is quite new, and and it's quite difficult. So anyway, so let me come back to the semi-orthogonal decomposition of this derived category now. So then the natural question is, okay, can he, how can I say, generalize this? I mean, can he give more proof, more evidence for this conjecture? And myself and Narasimhan prove that when R is 2 and degree is 1 and the C is non-hyperelliptic curve of genus greater than or equal to 16, so we need this technical condition because we use this Heck correspondence and the Narasimhan-Lavanan desingularization. And, so anyway, there are some technicality involved. So we need this condition, but we believe that we don't need condition. But anyway, we prove that the second symmetric product of derived category second symmetric product can be embedded into modular space. So we prove that we construct certain functor and prove that by pre-Mukhain transform, this gives some embedding. So indeed, we construct a certain vector bundle CF on this C second symmetric product times M, and we prove that the pre-Mukhain transform, whose kernel is this vector bundle, gives the embedding. And indeed, we prove that we prove vector bundles on this. We prove certain functor from derived category of K-symmetric product to the moduli space for any rank and degree and K. And our theorem says that, and we conjecture that these functors will give embedding under certain condition. And our theorem show the first evidence why that under certain condition, these functors really gives the embedding. Okay, so how can I say? Yeah, let me briefly record the okay, but how many times I have? So let me. Okay, I see. Okay, let me briefly explain how can we construct a functor. So I have this this diagram: C times C times C times M, and C to the K, and C times M, C times M. So I have a Poincare bundle here and here and here and here and here, and I pull back all these Poincare bundle to this C times C times C times C times M. Okay, then I consider this vector bundle E tilde on this C times M, and then there's very natural SK because this there's an SK action permitting the elements in the C to the K. So there's natural SK action on CK times M, and then this bundle, which is pullback of all this Poincare bundle, has natural SK action. So this bundle become natural SK equivariant bundle, and then it gives an element here. And then it is well known that this, how can I say, this category has the following semi-orthogonal decomposition, and E is an element here, and by definition, E has a projection to this category. E can be projected. E has a component which projects this category, and this is a way we produce this vector bundle on this CK times M. And so this is this is our pre-MKI function, and we prove that. This gives the embedding. And but how can I say? So far we just define this bundle, and then in order to prove the vanishing theorem, we use this cohomology vanishing using this Hecke modification. So, and then, so anyway, we construct the functors for any k and length r and d, and we conjecture that this pre-MKI transform will give embedding. And then recently, Tebelev and Torres and Su Yao use completely different method to obtain the semi-orthogonal decomposition. So we construct these functors and prove that this is embedding using Hecke modification. But Tebelev and Torres use this tedious flip and the variation of GIT and derived category. So they obtain the following result. And Su and Yao use another method to obtain the following semi-orthogonal decomposition. So they proved that the derived category of length 2 vector bundles on curve with the determinant L has the following semi-orthogonal decomposition. So derived category of M has this 2 copy of point, 2 copy of curve, 2 copy of G minus 2 symmetric product, and 1 copy of G minus 1 symmetric product. And but the problem is that they didn't prove that. They were not able to prove that this generate the whole category. So it is still mysterious whether this remaining part is trivial or not. So anyway, they constructed certain semi-orthogonal decomposition exists, and this semi-orthogonal decomposition field has all expected component, but still we don't know whether these generate the whole category or not. And the one point I want to also mention is that our technique also, so this technique use this tedious frame, but our technique between myself and Narashiman also can be generalized to higher rank case. So there are some, it's completely different method using complete different perspective. So anyway, yeah, in this sense we have this expected decomposition for certain story in length 2. Still we do not have complete picture, but recently there has been lots of progress. Okay, so is there any question so far? Okay, if not, let me go further. Okay, then as I told you, Narashiman and I believe that our technique also can be generalized to higher rank case. So what happened in higher rank case anyway? So can you generalize this length story we have seen to higher rank cases? So Gomez and myself have the following conjecture. So the derived category of moduli space will have the following semi-orthogonal decomposition, and each component should be the derived category of a product of symmetric product and Jacobian. So let me show you some evidence. And the motif of this vector, this motif of this moduli space also will have the compatible motivity decomposition. It's quite natural conjecture, of course. For rank is equal to 3 case, we have the following conjecture. We have the following explicit conjecture. So when rank is 3, then the derived category of this moduli space will have the following semi-orthogonal decomposition. So it has a semi-orthogonal decomposition whose component is symmetric product of two symmetric product of curve and symmetric product of curve. So we have, we have this following conjectural semi-orthogonal decomposition, and we have this very explicit term. Which component? Each which component should be there this way. And we have evidence for this conjecture, of course. So there's compatible motivic decomposition for rank equals 3 case. So when rank is 3 and degree is equal to 1, then we have the following identity in the completion of Grothendieck variety. Because we start from stack, we need this completion. But anyway, so we have compatible motivic decomposition in the level of Grothendieck variety. And we also prove that the same identity holds for completion of Chow motif and completion of Voivodskis motif, or triangulated category of geometric motifs. Okay, so I mean, and it is quite, when you see our proof, it is quite natural to expect that each component should be the derived category of products of CK and Jacobian. So yeah, let me give you several remarks. So yeah, in the level of Chow motif, we use another work of Banno's computation. And then for the same identity, we prove this identity in the Grothendieck variety, but there's a morphism from this completion of Grothendieck variety to completion of geometric motif. So we just apply this morphism, this morphism to here and obtain the corresponding motivic decomposition in the completion of Grothendieck variety. And the key point is that we treat the motif of symmetric product and Jacobian as if they are irreducible term. Motif of these varieties can be decomposed, so it's not irreducible term. But when you see the derived category of this variety, then as we saw, it is indecomposable. So this is key idea. So we use these terms as if they are irreducible terms, and we obtain this decomposition as by treating this term as irreducible component. And indeed, Lin's work was motivated by our treatment of these things. And we indeed conjecture that these are indecomposable, and he indeed proved that this is the case. And of course, we conjecture that we expect that there is corresponding decomposition in the other level, other category motif, not dealing with the completion. And we also conjecture that there must be some corresponding decomposition in the Foucault category and the quantum cohomology. And it was proven for rank 2 case. Rank 2 case, there is kind of evidence in the level of Foucault category. Okay, so anyway, we have this conjecture and this remark. And finally, let me quickly go to the semi-orthogonal decomposition of higher rank vector bundle. So far we discussed motif for higher rank vector bundles. And let me deal with the semi-orthogonal decomposition of this derived category of higher rank vector bundles. Okay, again, let me go back to the basic starting point. So starting point of all these works was the embedding theorem by Narashima and Kuznetsov and Fonarev. So saying that the derived category curve can be embedded into derived category of this moduli space when length is 2. And Bellman and Mukhopadhyay generalized the Narashiman's argument, and then they prove that the length prove that the embedding is true when length is greater than or equal to 3 and degree is 1 and genus is greater than or equal to R plus 3 case. So degree equal 1 and this genus restriction, anyway, then they prove that. And recently, we use completely different method to prove the embedding theorem. So Han-Bon Moon and myself proved that for any curve and any rank and any degree, the derived category of curve can be embedded into derived category of moduli space. So, like rank 2 case, we have one copy of curve in the derived category of moduli space for any rank and any degree and any curve. So we proved this result recently. So let me explain how we prove this result. So let's see a smooth projective curve of genus G, and we basically use the idea of parabolic bundle. So let's see a smooth projective curve of genus G, and let P1 to Pk be a set of distinct points in C. And the parabolic bundle is this kind of data. So I consider vector bundle on curve, and each point I have some flag. So each point, this is if this bundle has length r, then each point this is c to the k, c to the r, and I have some flag of subvector space in this CR on this point. So this is called the parabolic bundle, and I also can consider this parabolic weight to define stability condition. And then I define this parabolic degree and parabolic slope to say stability condition for these parabolic bundles. And then Mehta and Seog Lee constructed the moduli space of parabolic bundles on C using these data. So please recall that, I mean, by famous theorem of Nagashima and Seog Lee, the moduli space of a stable bundle is kind of a moduli space of representation, space of a fundamental group. And when I have this parabolic data, then I have this parabolic obifold fundamental group of C, and then I consider again representation, and then, I mean, we can construct a natural, I mean, it is quite natural to expect that the moduli space of parabolic, stable parabolic bundle, semi-stable parabolic bundle on this curve, and the Mehta and Seog Lee did the work. So anyway, from now on, let M be the moduli space of a semi-stable parabolic bundle with weight A. And then let me briefly explain how we prove this result, how we can prove that the derived category curve is embedded into derived category moduli space. The key idea is to prove that, to compute the following X group. So this EX means that I have, please recall that I have this Poincare bundle on C times M, and I choose a point X, and then I have this slice, and E is just a restriction of this Poincare bundle to this slice. So this EX is nothing but a vector bundle on this moduli space. So I need to consider this X between EX and EY. And using this description of parabolic bundle, this can be identified the homology of line bundle on this parabolic vector bundle when A is very small. Because A is very small, then there's no effect of parabolic slope. But when A becomes large, then parabolic degree can play a role. Anyway, so we need to compute this X group by famous criterion of Bondar and Euler, and this can be identified, this homology of this line bundle. And then by studying this birational geometry of moduli space of parabolic bundle, one can show that there's a certain weight B, so this is weight A, but there's a certain weight B such that this cohomology vanishes. And then using this variation of GIT and window technique developed by Harpen-Leistner and Ballard-Favero-Kachanokov, we can identify the cohomology here to the cohomology here, and we already know that this is zero. So this is key idea. So one can show that there's for length is 5 and degree is 2, then we can, this is wall chamber and we move this direction. So this is our starting point. And suppose that I have a B, weight B such that cohomology vanishes, then I crossing this wall and check that the cohomology can be identified. That's the basic idea. Okay, finally, let me mention a few words and finish. So this technique can be, so far I discussed the derived category and motif, but I believe that this technique has another interesting applications. So one application I want to mention is so-called constructing Asian bundle on this moduli space. As I told you, this moduli space is very well-known Fano variety, having many beautiful aspects. And recently, there has been lots of work studying Asian bundle on smooth higher dimensional varieties. So it is quite natural to ask whether this moduli space has an Asian bundle or not. So what we prove is that a vector bundle E on a variety V is Asian if it doesn't have a middle cohomology. I mean, if the variety has dimension n, and if I tensor this E with respect to this ample line bundles J, and if the middle cohomology all vanishes from I from 1 to n minus 1 and for LJ, then I will say this vector bundle is HM. And using this technique, studying derived category moduli space, we prove the following result. So this restriction EX, as I told you, EX is restriction of this Poincare bundle to this slide. We prove that for any curve and any rank and any degree, we prove that this EX become an HM bundle with respect to the generator of ample Picard group, the ample generator Picard group. So we found very natural family of HM bundle in this moduli space using this technique. Okay, let me stop here. Thank you very much.
Thank you.
Thank you very much.
Shall we have some questions? Maybe I'll stop the recording, that way people ask better.